Hello all. I'll be discussing a topic today in Discrete Mathematical Structures 18 CS36 Module 5 Introduction to Graph Theory. We'll discuss the definitions and examples in the introduction of graph theory. Myself, Dr. Madhura, working as an assistant professor, Department of Mathematics, Sai Vidya Institute of Technology, Bengaluru. Let us first see some basic definitions and later we will discuss the problems. We'll understand what is a graph. A graph is a pair V, E, where V is a non-empty set and E is a set of unordered pairs of elements taken from the set V. So we write down or we frame a graph with the pair V, E, where V represents a non-empty set and E is a set of unordered pairs of elements taken from the set V. For a graph V, E, the elements of V are called vertices or points or nodes, and the elements of E are called edges or undirected edges. The set V is called the vertex set and the set E is called the edge set. So a graph is in turn a pair V, E, where V is the vertex set and E is the edge set. The graph V, E is also denoted by G equal to V, E or G equal to G of V, E or simply G. Let us discuss what is a null graph. A graph containing no edge is called a null graph. So we have only the vertex set, but the edge set is empty. Such a graph is known as null graph. Next, we'll take up an example for null graph. So this is an example for a null graph where you can see only the vertices where the edge set is empty. Here, V equal to A, B, C, they are the vertices. V is the vertex set and there are no edges. Edges are nothing but the lines joining the vertices. So there are no edges at all. So edge set is empty. Next, trivial graph. A null graph with only one vertex is called a trivial graph. An example. So there's only one vertex in the graph and the vertex is named as the vertex A. This is a trivial graph. So here the vertex set V equal to A and the edge set is empty. Finite graph. A graph with only a finite number of vertices and edges is called a finite graph. Otherwise, it's an infinite graph. So countable number of vertices and edges must be there in a graph. Such a graph is called a finite graph. Otherwise, it is an infinite graph. Next, we'll see the definition for order and size. The number of vertices in a graph is called the order of the graph and the number of edges in the graph is called its size. So order represents the total number of vertices in any graph and size represents the total number of edges in the graph. In other words, for a graph G equal to V, E, the cardinality of the set V denoted by the symbol, so V under two parallel lines, is called the order of G and the cardinality of the set E denoted by capital E under two parallel lines is called the size of G. A graph of order n and size m is called a n, m graph. So usually we represent the total number of vertices in the graph by the word order, which is nothing but cardinality of V. Similarly, the total number of edges in the graph is usually represented by the word size, and it is usually denoted by cardinality of E. So number of vertices is N and number of edges is M. So in general, a graph of order N and size M is called a N, M graph. End vertices. If Vi, Vj denote two vertices of a graph, and if Ek denotes the edge joining Vi and Vj, then Vi and Vj are called the end vertices of Ek. So suppose I have an edge E wherein the end vertices are V1 and V2, then E will be the edge whose end, which is joined by two vertices V1 and V2. So those vertices V1 and V2 are called the end vertices of the edge E. Example. So here we can observe E1 is the edge joining two vertices A and B. So A and B are called the end vertices of the edge E1. Loop. An edge whose end vertices are one and the same is called as a loop. The starting vertex and the ending vertex are the same here. So end vertices are one and the same. So we represent an edge in this manner. So I have a vertex A. We are starting from A and coming back to A. The end vertices are same. A loop is an edge. So this is an edge for us. This represents an edge for us. And for this edge, starting and the ending vertex is the same. Such an edge is called a loop. Next we have parallel edges. Two edges which have the same end vertices are known as parallel edges. So an example like this, A and B are the two end vertices. I have drawn two edges between A and B. There are two edges joined from between A and B. So two edges which have the same end vertices are known as parallel edges. Next, we'll know about multiple edges. If in a graph there are two or more edges with the same end vertices, then the edges are called multiple edges. So suppose in a graph, two or more edges are having the same end vertices, then such edges are called multiple edges. Example, we can see two vertices A and B here, and we can see 5 edges are joining A and B. Simple graph. A graph which does not contain loops and multiple edges is called a simple graph. So a graph which do not contain any loops or any multiple edges, then such a graph is called a simple graph. I have taken up an example of 3 edges and 3 vertices ABC here, which is a simple graph without any loops and multiple edges. Next, we will understand the definition for multigraph. A graph which contains multiple edges but no loops is called a multigraph. So there are multiple edges but the graph do not contain any loops is called a multigraph. So you can observe in the example below that A to D there are 2 edges joining and there are no loops in this graph. So such a graph is called a multigraph. Next we will understand the definition for general graph. A graph which contains multiple edges and or loops is called a general graph. So any graph which may contain multiple edges and it may also contain loops, both might be there or any one of them might exist in the graph, then such a graph is in general called as general graph. So an example for the same is taken here. So we have edges joining A to B. There are two edges joining here and there is a loop from A to A. So this is a example for a general graph. Next, we will see the definition for incidence. When a vertex V of a graph G is an end vertex of an edge E in a graph G, then the edge E is incident on the vertex V, or it is also called as incident to the vertex V. So any vertex V is an end vertex of a particular edge means then that edge is known as is incident to the vertex V. Since every edge has two end vertices, every edge is incident on two vertices, one at each end. So every edge, whenever you are trying to join an edge, it has two end vertices. So every edge is incident on two vertices, one at the each end. The two end vertices are coincident if the edge is a loop. So if you are starting and ending at a particular vertex, then the end vertices are coincident. Then such a edge is called a loop. Next, we will understand adjacent vertices. Two vertices are said to be adjacent if there is an edge joining them. The adjacent vertices are also known as neighbors. So any two vertices are said to be adjacent if there is an edge joining between them. Similarly, adjacent edges. Two non-parallel edges are said to be adjacent if they are incident on a common vertex. So two edges, they are coming and incident on a particular vertex, then such edges are called as adjacent edges. They are always non-parallel edges. That is, if they have a vertex in common. So two edges are joined to a particular vertex, then such an edge is called adjacent edges. Example. In the example shown here in this graph, I have considered four vertices A, B, C, D, and there are three edges in the graph E1, E2, E3. We can see that A and B are the adjacent vertices. Because they are joined by an edge E2, we can say that A and B are the adjacent vertices. We can also say that E1 and E2 are adjacent edges because we can observe that E1 and E2 are incident on a common vertex A. So E1 and E2 are known as adjacent edges. Next, we'll understand the definition for complete graph. A simple graph of order greater than or equal to 2 in which there is an edge between every pair of vertices is called a complete graph or a full graph. It is usually denoted by Kn. So, complete graph is always defined for number of vertices greater than or equal to 2. And the graph has to be a simple graph without any loops and multiple edges. So if there is an edge between every pair of vertices in a simple graph, then we say such a graph as a complete graph or a full graph denoted by Kn. So a complete graph with 2, 3, 4 and 5 vertices are shown here. So I have taken 2 vertices. So that is why the graph is denoted by K2. N is taking the value 2. There is an edge between every pair of vertex. There's only one pair of vertices here, so we need to draw by an edge. Next, I've taken K3. So 3 vertices and joining all the 3 vertices by the edges, we can draw the graph for K3, which forms a triangle. Then we have K4. So 4 vertices are considered. There should be an edge between every pair of vertices. So if you consider this as one pair, there should be an edge between it. Another pair of vertices, there should be an edge between. So like that, we are trying to consider and draw K4, a complete graph with 4 vertices. Similarly, K5 with 5 vertices joining every pair of vertices by an edge. A complete graph with 5 vertices is known as Kuratowski's first graph. There's a special name for K5, a complete graph with 5 vertices. So K5 is called as Kuratowski's first graph. Next, we understand the definition for bipartite graph. Suppose a simple graph G is such that its vertex set V is the union of its mutually disjoint non-empty subsets V1 and V2, which are such that each edge in G joins a vertex in V1 and a vertex in V2. Then G is called a bipartite graph. So here we consider two bipartites or two disjoint vertex sets V1 and V2. Their union will be equal to the vertex set V, which is there in the simple graph G. And we join each edge in G with a vertex in V1 to a vertex in V2. This also means that no two vertices of V1 are joined by an edge. Similarly, no two vertices of V2 are joined by an edge. So every edge in G should be joining from V1 to a vertex in V2. Then such a graph is called a bipartite graph. If E is the edge set of this graph, the graph is usually denoted by G equal to V1, V2, E. And the sets V1 and V2 are called the bipartites or the partitions of the vertex set V. So since we are going to divide into two disjoint non-empty subsets V1 and V2, we have divided into two particular vertex sets, and that is the reason V1 and V2 are known as bipartites or the partitions of the vertex set V. For example, consider the graph G shown below, for which the vertex set V equal to A, B, C, P, Q, R, S. And I've considered the edge set E as edge between A to P, A to Q, and then AR, BR, CS, and CQ. So this is the graph that I've considered. We observe the vertices are A, B, C, and another set of vertices are P, Q, R, S. So I have assumed V1 as the vertex set which consists of the vertices A, B, C, and V2 as another vertex set which consists of the vertices P, Q, R, S. And we observe that a vertex from V1 is joined to a vertex in V2. And no two vertices of the same set, of the same vertex set, are joined by an edge. These edges are joined by an edge, that is AP, AQ, AR are joined here. So V is the union of the subsets V1, which consists of ABC, and V2, which consists of PQRS. They are such that V1 and V2 are disjoint. There is no common between the vertex sets V1 and V2. So every edge in G joins a vertex in V1 to a vertex in V2. G contains no edge that joins two vertices both of which are in V1 or V2. That is what I mentioned. So there are no two vertices in the vertex set V1 joining by an edge. Similarly, there are no two vertices in the vertex set V2 joined by an edge. So such a graph has V1 and V2 as the bipartites. Next, We'll understand the definition for complete bipartite graph. A bipartite graph G equal to V1, V2, E is called a complete bipartite graph if there is an edge between every vertex in V1 and every vertex in V2. So firstly, the graph has to be a bipartite graph. So it has to satisfy all the conditions that we looked into in the definition for a bipartite graph. So being a bipartite graph, now we are going to join every edge in V1 to every other edge in V2. Then such a graph is called a complete bipartite graph. So I've taken up some example to show complete bipartite graphs. So I've taken K13 here. So there's one vertex in the middle which is joined to three other vertices. Similarly, K15, one vertex in the middle is joined to five other vertices. K23, so on the left part you can see two vertices joined to three other vertices. And there should be an edge between every vertex of V1 to every other vertex of V2. And obviously, no two vertices of V1 are joined by an edge and no two vertices of V2 are joined by an edge. Next, we also have considered K33. Three vertices are joined to three other vertices. Every vertex in V1 should be joined to every other vertex in V2. So complete bipartite graph is usually having the bipartites V1 and V2 and they respectively contain R and S number of vertices in it with R less than or equal to S. And the complete bipartite graph is usually denoted by K suffix R comma S. So in this graph, each of the R vertices in V1 is joined to each of S vertices in V2. There are R number of vertices in V1 and there are S number of vertices in V2. And we observe that each R vertices in V1 should be joined to each of the S vertices in V2. And thus there are R plus S vertices and R into S edges in the complete bipartite graph KR comma S. So the order is R plus S and the size is R into S. And hence we can represent KRS is a R plus S comma RS graph. Order is nothing but the number of vertices in the graph. So total number of vertices in such a complete bipartite graph will be R plus S and total number of edges is usually denoted by size of the graph and it is equal to R into S for a complete bipartite graph. There's a special name for K33. So K33 is usually known as Kuratowski's second graph. Now we will look into problems on the basics of graph theory. First question, if G is a simple graph, prove that 2 into cardinality of E is less than or equal to cardinality of V square minus cardinality of V. Total number of edges is usually denoted by cardinality of E and total number of vertices in the graph is denoted by cardinality of V. So we need to prove the resultant 2 into m is less than or equal to n square minus n. N is nothing but the order of the graph, that is number of vertices, and m is nothing but the number of edges in the graph, which is cardinality of E. Let us see the solution. In a simple graph, there are no multiple edges. From the definition we have learned this. A simple graph do not have any loops or multiple edges. Each edge of a graph is determined by a pair of vertices. So whatever the edges we are drawing in a simple graph, they are determined by a pair of vertices. Every edge is joined to two vertices only. For a pair of vertices, we have only one edge. That is the meaning of this. So for every pair of vertex, we have only one edge. So two vertices corresponds to one edge, we can say. Hence, for a simple graph with order greater than or equal to 2, number of edges cannot exceed number of pair of vertices. Since we do not consider any multiple edges or loops, the number of edges in such a simple graph can never exceed number of pair of vertices. The same can be symbolically written as m is less than or equal to nc2. Number of edges is nothing but m. They cannot exceed is symbolically represented as less than or equal to, and the number of pair of vertices. So out of n vertices, we are selecting a pair. So that is why it is nc2. So number of pair of vertices that can be chosen from n vertices is nc2. Now we will expand nc2 with the formula for NCR combinations. So n factorial divided by n minus r factorial into r factorial. Here r value is 2. So m is less than or equal to n factorial divided by n minus 2 factorial into 2 factorial. So m is less than or equal to, numerator can be expanded as n into n minus 1 into n minus 2 factorial. Denominator I have retained as it is. So this simplifies to m less than or equal to n into n minus 1 divided by 2. Cross multiplying 2 to the other side, we obtain 2m is less than or equal to n square minus n. 2m is less than or equal to n square minus n. The same can be symbolically written as 2 into cardinality of E is less than or equal to cardinality of B square minus cardinality of V. N is nothing but the number of vertices. M denotes the number of edges. So we have proved the result in that for a simple graph, 2 into number of elements in the edges set is less than or equal to number of elements in the vertex set whole square minus number of elements in the vertex set. That is 2m is less than or equal to n square minus n. Second problem. Show that a complete graph with n vertices, that is kn, has half of n into n minus 1 edges. So given graph is a complete graph, we'll recall the definition for a complete graph, that there should be an edge between every pair of vertices. So we have to prove that it has half of n into n minus 1 edges. Solution. In a complete graph, there exists exactly one edge between every pair of vertices. So there is an edge between every pair of vertices means that it has exactly one edge only between every pair of vertices. And therefore, the number of edges in the complete graph is equal to number of pair of vertices. So total number of edges in a complete graph will be always equal to the number of pair of vertices that exist in the complete graph. Symbolically, number of edges is nothing but m, and number of pair of vertices means we are selecting two vertices out of n vertices. This is equal to expanding nc2, we get n factorial divided by n minus 2 factorial into 2 factorial. Numerator n factorial can be written as n into n minus 1 factorial into n minus 2 factorial, the whole divided by n minus 2 factorial into 2. So that n minus 2 factorial gets cancelled and we have m equal to n into n minus 1 divided by 2. N into n minus 1 divided by 2. So this says that in a complete graph with n vertices, the number of edges, that is m, number of edges is equal to half of n into n minus 1. And this is the required resultant we had to prove. Moving ahead to the next problem. Question. Show that a simple graph of order 4 and size 7 and a complete graph of order 4 and size 5 do not exist. So this is an application of the previous two results, what we proved. We proved the resultant in the first problem that for a simple graph, m is less than or equal to half of n into n minus 1. And in the second problem, we proved the result in that for a complete graph, number of edges m equal to half of n into n minus 1. So using those results of the number of edges based on, we have to prove this problem. We need to show that for a simple graph of order 4 and size 7 and complete graph of order 4 and size 5 does not exist. We'll prove one by one. The first resultant is for a simple graph and it is given that order is 4 and size is 7. So n equal to 4 and m equal to 7 is mentioned. We write down the result for a simple graph that 2m is less than or equal to n square minus n. This is the relation between n and m. So considering this result, substituting the values of m and n, we have 2 into 7 is less than or equal to 4 square minus 4, which is 14 less than or equal to 12, which is a false expression. Left hand side, we obtain 2 into 7, which is 14. Right hand part, we obtain 4 square minus 4, which is 12. And 14 is a larger value. It is never less than or equal to 12. So, such a graph do not exist. That is, a simple graph of order 4 and size 7 do not exist. Similarly, for a complete graph, it is given that order equal to 4 and size equal to 5. So, n equal to 4 and m equal to 5 is mentioned. We consider the expression for complete graph, what we proved in the last problem. That is m equal to half of n into n minus 1. M is given as 5, n value is given as 4. Substituting and simplifying, we obtain 5 is equal to 6. 5 is a value never equal to 6. So this is also a false expression. The meaning of saying that it is a false expression is that a complete graph of order 4 and size 5 does not exist. So for the given values of n and m in both a simple graph and a complete graph, we have shown that such a graphs do not exist. Next problem. How many vertices and how many edges are there in the complete bipartite graphs K47 and K711? We recall from the definition that complete bipartite graph is usually denoted by K, R, S. So R and S values are given. R is nothing but the number of vertices in the vertex set V1 and S is nothing but the number of vertices in the vertex set V2. So number of vertices are given for us. So K47 and K711. We have to find out how many vertices and how many edges does exist in these two graphs. That's the first subpart of the question. Secondly, if the graph KR, 12 has 72 edges, then what is the value of R? So the second graph, that is having vertex at V2, is given as 12. R is not given for us. And the graph consists of 72 edges. So we need to find the value of R. Let us do the solution. A complete bipartite graph KR, S has R plus S number of vertices and R into S number of edges. Complete bipartite graph is having two mutually disjoint vertex sets V1 and V2. So number of vertices in V1 is denoted by R and number of vertices in V2 is denoted by S. And this resultant, we learned it from the theory that KR, S has R plus S number of vertices and R into S number of edges. First part of the problem. It is given that we have to find K412, K47 has how many number of vertices and how many number of edges. So R and S is equal to respectively 4 and 7. So the graph K47 has 4 plus 7, that is 11 vertices totally, and 4 into 7, which is 28 edges. Similarly, the graph K711 has 7 plus 11, which is 18 vertices, and 7 into 11, which is 77 edges. So since we knew R and S, we just applied the formula that total number of vertices in the complete bipartite graph is R plus S, and total number of edges in the complete bipartite graph is R into S. So using that, we have obtained K47 has 11 vertices and 28 edges, and K711 has 18 vertices and 77 edges. This was the first part of the problem. Second part, it is given that KR, 12 has 72 edges and we need to find the value of R. That is, number of vertices in the vertex set V1 is to be found. So given that the graph KR, 12 has 72 edges, we consider the total number of edges in the complete bipartite graph is equal to R into S. So M is nothing but the total number of edges, which is R into S. M is known to us. The complete bipartite graph KR12 has 72 edges, so M equal to 72. R is not known to us, and there are 12 vertices in the vertex set V2. So S is equal to 12. So we have 12 into R equal to 72. Dividing throughout by 12, we get the value of R as 6. That was the second part of the problem, to find R, given that KR12 has 72 edges. So we obtain R value as 6. So I've given some practice questions. Maybe practicing these problems will help you to have more clarity on the basics of the graph theory. We need to remember these expressions in the basics. For a simple graph, we proved the resultant 2m is less than or equal to n square minus n. For a complete graph, we have number of edges is equal to half of n into n minus 1. For a bipartite graph, the relation between m and n is 4m is less than or equal to n square. And for a complete bipartite graph, KR, S, there are totally R plus S vertices and R into S number of edges. So these points will help us to do more number of problems on the basics. Thank you for watching.